So section 4.3. So what we're going to talk about today all has to do with angles in triangles. So I'm going to draw a generic right triangle here. And we're going to call this angle theta. And since we're talking about angles in triangles, we're going to say that 0 is less than theta, less than 90 degrees. So we're talking about angles between 0 and 90 degrees because we're talking about angles in triangles. Generally, when we're working with triangles, our angles are going to be in degrees. So I said usually in trigonometry, we work with angles in radians, except when we're working with triangles. Then our angles are usually in degrees. What we're going to be using today is SOHCAHTOA. What we learned whenever you learn SOHCAHTOA. Geometry a little bit, algebra 2 some. So what I do is I label the sides of the triangles. So this is going to be our adjacent side, adjacent to the angle, the opposite side, and the hypotenuse. And we're going to write our trig functions. So we're kind of getting away from thinking of our trig functions having to do with coordinates on the unit circle. We can still think of that, but we're going to define our trig functions, our trig quantities, as ratios of sides of a right triangle. So I'm going to say, and hopefully these quantities are familiar, sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse, and tangent theta is opposite over adjacent. And then our cofunctions are the reciprocals. So cosecant theta is hypotenuse over opposite. Secant theta is hypotenuse over adjacent. And cotangent theta is adjacent over opposite. A couple of reminders here. When we write, often students want to leave off the theta or the t or the x or whatever. So when we write this, what we're saying is we're thinking of this sine theta. What we're actually doing is saying the sine of theta. So it doesn't make sense to say the sine equals square root of 3 over 2. You need the sine of something. So a lot of times students like to drop off the whatever. Saying this is kind of like saying square root equals 10. Square root of what equals 10? It doesn't make sense to say square root equals 10. Also, you should never do this. So I'm going to write this in red. You can't do this because that's a sin. Okay, don't do that. And you can also not do this. That doesn't work. No, don't do those. Just so you know. Okay. All right. So a type of questions on this so far? So a typical problem that you might see that has to do with these ideas is it might ask you, I'm just going to go down here, if, let's see, what do we want to do? We'll have a triangle, like so. And here's my theta, and this is 15, and this is 8. And the problem might say find the exact value of the 6 trig functions. So those two words, exact value, that's a clue that this is not a calculator problem. We're not plugging this into our calculator. The other clue might be that this shows up on a portion of the test that you can't use a calculator on. Exact value should always tell you that you can do it without a calculator. So what this is saying is write all of these ratios. So the way I think of these, I either mentally or I actually write it down. I label the sides of the triangle. So this is my adjacent side. This is my opposite side. But I don't have a value for the hypotenuse. What do I do? What always works for a right triangle? Pythagorean theorem. We can always use a Pythagorean theorem on a right triangle. So we can use the Pythagorean theorem, or sometimes we get nice Pythagorean triples. Does anyone off the top of my head, top of your head, know what the third in that Pythagorean triple is? Turns out to be 17. Well, we can always say c squared equals 8 squared plus 15 squared. So c equals the square root of 8 squared plus 15 squared. And we could calculate that out. And we'd see that's 17. Sometimes the book will give you a nice Pythagorean triple. And then we can write our ratios. So I'm not going to write them all out. So we can say sine theta is opposite over hypotenuse, 15/17. Cosine theta is 8/17. And I'm going to say, etc. So we can write all 6 of them. And once we write sine, cosine, and tangent, the rest are just the reciprocals. When we see an expression like this, we can always think of these two numbers in this ratio as the sides of a right triangle. So we can always think of that this way. We can draw a triangle and find our missing side. So if we know one of the trig functions, we can find all 5 of the rest by drawing the triangle and finding the missing side. And when you can think of these ratios as sides of right triangles, it's kind of second nature. That really helps with the trigonometry some of the trigonometry that we're going to do moving forward. So these ratios always give us 2 sides of a right triangle. All right, let's talk about a couple of other things. Kind of add a layer here, and then we'll do some examples. So I want to write out a couple of sines and cosines. So sine of 60 degrees. What is the sine of 60 degrees? 60 degrees up here. Sine is the y coordinate, so that's going to be the long side of the square root of 3 over 2. And the cosine. 6 degrees is 1/2. Short side of that triangle. What's the sine of 30 degrees? 1/2. And the cosine 30 degrees? Square root of 3 over 2? What is there anything special about 30 degrees and 60 degrees and how they're related? They're x's and y's, yeah. It's a special right triangle, so let's draw a triangle. They are a special right triangle, and I'm looking for a more general relationship. So let's say that's my 60-degree angle and that's my 30-degree angle. What do they add up to? Well, just 30 and 60 add up to 90. They're complementary. And what happens with our sines and cosines here? They're flipped. That relationship is always true for complementary angles. So I'm going to just draw a little arrow here. That relationship is always true for complementary angles. And the reason is, in my right triangle, the opposite side for the 60-degree angle is the adjacent side for the 30-degree angle. So the opposite and the adjacent, depending on where the angle is, they switch around. The way that we write this algebraically, I'm going to call it our cofunction identities. So the cofunction of complementary angles are the same. So the way we write that is that the sine of 90 degrees minus theta, that's how we find the complement of theta, that equals the cosine of theta. That's what we have here. That's true for the tangent also. Tangent 90 degrees minus theta is the cotangent of theta. The secant 90 degrees minus theta is the cosecant of theta. And it also works going the other direction. Cosine of 90 degrees minus theta is the sine of theta. Those are complementary angles. That's what we have going on here. The cotangent, 90 minus theta, is the tangent of theta, and this one the other way around also. Cosecant of 90 degrees minus theta is the secant of theta. So we always have those relationships with complementary angles, the trig function and its cofunction. All right, we good there? These identities, this relationship, it doesn't come up often, but it does come up occasionally, and when it does, it's very nice to be able to use it. All right, let's look at a couple of examples. Kind of typical right triangle trigonometry problem. I'll talk about how we set up one of the problems that's going to show up in your homework, and then I want to give you just a reminder about doing trig functions in your calculator. All right, so a typical example might be the sun is up 30 degrees from the horizon. And this is also a good example of when you're a good math student, when you go camping, the supplies you should have. So you're camping. You notice the sun is 30 degrees up from the horizon. Well, of course, you have your little instrument to measure to measure angles. So the sun is 30 degrees up from the horizon. It's shining on a tree. And the tree is casting a 50-foot shadow. So before you went camping, what you've done is you've measured your pace, so you can count your steps, and you know you can measure distance that way. So it's casting a 50-foot shadow, and being a curious person when you're camping, you want to know how tall is a tree. So let's draw a picture. That's my favorite part about these kinds of problems, other than thinking about camping supplies. There's the sun. There's my tree. And the sun is shining. There's a ray of sunlight, hits the tree, and that ray goes down and hits the ground here. Well, here's the shadow. It's where the tree is blocking the sun from hitting the ground. And it says the sun is up 30 degrees. We're also assuming that the tree this is a nice healthy tree, so it's growing at a 90-degree angle from the ground there. We know the shadow is 50 feet long, and we want to know h, the height of the tree. Well, we're good pre-calculus students. We say, oh, we can just use some trigonometry here, figure out the height of the tree. So I look at this triangle, and I have the opposite side and the adjacent side. So what trig ratio am I going to use? Tangent has to do with the opposite and the adjacent. So the way I would write this is tangent 30 equals the opposite over adjacent. So our height is 50 tangent 30. And being very good pre-calculus students, we realize we don't even need a calculator for this problem, because 30 degrees is a unit circle angle. So we know the tangent, or we can figure out the tangent of 30 degrees. So anybody remember it or have your chart handy? Tangent of 30 degrees? Or you can do sine over the cosine. Sine is 1/2, cosine is square root of 3 over 2. Divide, you get 1 over the square root of 3, which is square root of 3 over 3. So I would say, also being very good calculators, we would realize we don't even need a calculator for this, because square root of 3 is about 1.73, and square root of 3 over 2 I know is about 0.866. So square root of 3 over 3 is a little less than 0.8. So this is going to be a little more than 25 feet. If we calculate this out, if we had a calculator with us when we were camping, we'd see that this is 28.87 feet. So this is kind of a typical right triangle trigonometry problem. And I know the way I drew my picture, my ray of sun isn't straight, but that's just, I'm a math student, not an art student. So. All right, questions on that example? All right, there is one problem, similar kind of problem where you want to find the height of a cliff. But in this setup, I'll just talk about the setup for this problem. You have a cliff or something that you're trying to figure out the height of, and you measure this angle, and then you walk a little distance closer and you measure this angle again. I'll call this theta 1 and theta 2. So there's a problem like this in your homework. And this is a vertical cliff. What you have to do for this kind of problem is you set up one equation using this triangle, the big one. And you set up another equation. You'll be able to write two equations like we just did on the last problem for that smaller triangle. You will have two equations and two variables. So you end up using a system of equations. And this one, I think it's easier to solve by substitution. So we're pretending, for this problem, we're pretending that we don't know law of sines or law of cosines. Technically, we haven't learned it yet. So we're using right triangle trig on this. So when you see that problem, it's two equations with two variables. All right, last thing I want to talk about is if we had a problem like this. Sine of theta equals 0.357. And we want to know what theta equals. So we know what the sine is. We want the angle. How do we, in our calculator, how would we figure out that angle? Inverse sine. So in your calculator, you're going to say the theta equals, I'm just going to draw the button here. This is where you use the sine minus 1 of 0.357. And if you plug that in your calculator, if your calculator is in radian mode, you'll get this answer in radians. So that's going to be approximately 0.356 radians. If it's in degree mode, it'll give you your answer in degrees. It'll be about 20.92 degrees. So if you want to find an angle, you have to use the inverse sine button. What if your problem said something like this? Cosine of 16 degrees, 18 minutes. What would we do here? Any ideas? Well, don't we have a nice way that we talked about before? Convert this to a decimal using your second apps, your angle menu. So convert that angle to a decimal first and then find the cosine. So your calculator, I think otherwise your calculator doesn't like it. So when you see those degrees, minutes, seconds, convert it to a decimal and then work with it. I think there are a couple of problems where they give you the angle in degrees, minutes, seconds. Just to remind you that you can do that in your calculator. All right, questions? Okay. Our homework? Whoops, sorry. I wanted to click the other button. There's that.